Welcome. In this session in linear data analysis, we'll explore how standardization of data works with linear regression. So let's consider a simple set of data. Let's consider we'll have M data in one column, and we'll use an intercept term. And what that means is our data matrix is A, and that will be, if there's M data with one column, we'll have a size M vector of independent observations, and then to handle the intercept term, we'll have the ones vector. And our linear regression will be that A times some weight vector, W1, W2, is approximately our dependent observations. Now, let's try the zero mean form. So, in standardization, the first thing we do is make the data zero mean, and then the second thing we do is make them both, all of the data have unit variance. So use zero mean data. And that means there are two parts to the data. There's the independent and the dependent observations. And so on the independent side, that will be a matrix that we usually represent as M. And that will be A minus the mean of A, which will represent that as a vector M. And what's the average value of the ones vector? Well, that would be 1. What's the ones vector where each term has that term minus 1? Well, that would be the 0 vector. And that looks like that's going to be a problem, because that's not linearly independent anymore. And then, well, let's continue. So we've taken the zero mean form of our data vector. Now we have to take the zero mean form of our dependent observations, and let's call that Y. Actually, let's call that B. And let's say that that is C minus C bar. And strictly speaking, that should be with a ones vector. So now, what is our regression? Well, it looks like we would have, so let's ask ourselves, do we have, because the moment we see a 0 there, we know that we're violating some of the assumptions. Do we have M times, let's say, our new weights, because they're not going to be the same, MV, is that approximately equal to B? Well, if I expand that out, that would be M times the 0 vector times V1, V2, and that would equal V1 times M plus V2 times 0, and we cannot determine V2. And we rarely do this. Let's put an exclamation point, because that's a big problem. So what we need here, we need a simpler model. And the reason is that the deep reason is that when we included an intercept term and then we did the zero mean, because it went to 0, that means that the intercept term is too complicated. So instead, what we want is this. So our new model is, we'll say that the M vector times, now if a size 2 vector was too complicated and messy, that means we need a size 1 vector, which is just a scalar. So let's call that scalar value U. And we'll say that that's approximately equal to our zero mean dependent observations. Okay, so now so that's the new model, okay, and in the end we want to equate, okay, so this needs to be the same as. So what was our original regression model? Our original regression model was that A times weight 1 plus weight 2 is approximately the dependent observations. So now let's expand out this one. M times U being approximately equal to B, well, that's the same as, what is M? Well, that is the independent values minus the mean of the independent values times the ones vector times U, and that will be approximately equal, and then B was C minus the average of the dependent observations times the ones vector. And what is that the same as? Well, let's multiply U into all of this. So that's equivalent to A times U plus, this will be plus negative A mean ones vector U, and that's approximately equal to C minus the mean of C times the ones vector. Let's take this part over here, and that would be equivalent to A times U plus, now I expand this part, so now when I take that over it's positive, so that's C1 minus A bar 1 U is approximately equal to C. And now I've taken this zero mean regression and I put it in the same form as the original linear regression. So we can now find, so this is a good one, we can find, so what is W1 from our original regression? Well, W1 is the thing that's multiplied by A, so that means that W1 is the same as our U parameter. And what is W2? Well, that was the intercept term, and so the intercept term for our original problem can be found from the zero mean as, this will be the average dependent value times the ones vector minus the average independent value times the ones vector times whatever value comes out of that. So what we would actually do is this. We would set up M times U is approximately B. We would solve that using the normal equation, and that would give us a value for U, and from that value for U we could then recalculate our values for W1 and W2. So that would let us work. Now, what about standardization? Standardized data. Well, those are, we divide the zero mean data by the standard deviation. And we are writing the standard deviation as the Greek letter sigma. So what this does is this scales each side. And what that, So let's now represent our transformations. We'll say that x, which is x is now a convention in machine learning and a lot of statistics, is that x is a zero mean unit variance form of your original data. So x is our zero mean data was in the vector m, and we divide that by the standard deviation that we calculate. And now y is our standardized dependent observations, so that will be our b vector divided by the standard deviation of everything in the b vector. And the setup is that we want to equate, so we want to equate our regression on the zero mean data was the zero mean data times u was approximately the zero mean dependent data. And now we want to equate that with x, let's use the symbol z, is approximately the standardized form of the dependent data. And we can now do this by just substitutions. So the way that we would do that is we would say that, let's leave ourselves a little room here, that x times z is approximately y, and that's equivalent to saying that m, so let's take m, so x is m over sigma m, so m over sigma m times z is approximately, and y is b over the standard deviation of b. Then we can take this term over here and we can say that that is the standard deviation of b times m divided by standard deviation of m times z is approximately b, and we're almost there, because now to get this to be in a pure term, we would say that this is m times, let's factor all of this into one thing, which is the standard deviation of b divided by the standard deviation of m times z is approximately b. So that implies that we can find our scalar u as we can take the standard deviation of b, divide by the standard deviation of m, and multiply that by the value z. So the way that we would handle standardized data is this. We would get the standardized data in the form x and y, so that we would then solve this regression. X, z is approximately equal to y. We would find z by using the normal equations. From z and the standard deviations, we would compute u. From u, we would then use the zero means and calculate the slope of our linear regression and the intercept term for our linear regression. And so we can use standardized data to perform a linear regression, and then we can reconstruct our original weight vector, which are the parameters of our model.